In today's lesson, we are going to be looking at determining a quadratic equation given the roots and a point. So again, we're looking at quadratics, we're looking at the quadratic equation, we're looking at the different forms of quadratics. This one is going to be looking at factored form because we're dealing with roots and a point. So before we get into that, let's just kind of review our previous lesson where we had to use the quadratic formula to find the exact roots. So again, remember the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So we have our a, our b, and our c value here. It's already set equal to 0, so we don't have to worry about that. We can just plug in our values and solve. So negative b, or negative 4, plus or minus the square root of negative 4 squared minus 4 times 2 times negative 3. Divided by 2 times 2. X equals, the negative 4 can just become 4, plus or minus the square root of 16, 8 times 3 plus 24, divided by 4. X is equal to 4 plus or minus the square root of 40 divided by 4. We can simplify this using what we know about radicals. So we can make it 4 plus or minus root 4 times root 10 divided by 4. X is equal to 4 plus or minus 2 root 10 divided by 4. I can factor out on the top. So let's bring this up over here. I can factor on the top. X equals 2 times 4, or not 4 anymore, because we factored it. 2 times 2 plus or minus root 10 divided by 4. And simplify by canceling out the factor. 2 plus or minus root 10 divided by 2. So then we have two possible answers. X equals 2 plus root 10 divided by 2. And x equals 2 minus root 10 divided by 2. Again, because it's asking for exact values, we're going to leave it in this radical form. But these would be our two solutions, or our two exact roots. So just to review the factored form, we talked about these different forms before. The equation of a parabola in factored form is y equals ax minus r times x minus s, where r and s are your x-intercepts, or your zeros. So if you're looking at a parabola, this could be r and this would be s. And that's all we're saying about those two values. Again, remember that the value inside the bracket is opposite of what we see, right? So because the equation itself is x minus and r and x minus s, if we put a positive root in, it still stays as minus. Now in this lesson, we're going to be looking at how to determine the equation in standard form, or determine the equation given the x-intercepts and a point. And what we do is we plug the values for r and s, or our x-intercepts, into the equation and simplify, if possible. Then we plug in the values of the point, the x and y, and solve for a. That would give us it in factored form, and if we needed to, then we could expand to write it as in standard form. So determine the exact equation of a quadratic function with zeros at 2 and negative 2 containing the point 0, 3. So because we know our zeros of 2 and negative 2, that's going to go into our equation ax minus 2 and x plus 2. So that just comes right from our factored form, kind of working backwards. Now we're going to substitute a point in. So now we're going to substitute this point in over here of 0, 3. So that means the x is 0, the y is 3. So 3 equals a times 0 minus 2 times 0 plus 2. So these values just came from the point. 3 equals a times negative 2 times positive 2. 3 equals a times negative 4. To get a by itself, I move the negative 4 over. It becomes 3 divided by negative 4, or negative 3 over 4. That is now our a value. So then I can write our equation in standard form. Or sorry, factored form. We'll start with factored form first, sorry. So in factored form, it would be y equals negative 3 over 4, x minus 2, x plus 2. If we want it in standard form, we would have to expand this. So y equals negative 3 over 4. And this entire portion here is actually a difference of squares. So if I wanted to expand that or multiply that, it'd be x squared minus 4. And I multiply my a value through, I get negative 3 over 4 x squared plus 3. So this is the equation in standard form. Again, same idea. We're going to go through this. Given our zeros, we're going to plug in it into our factored form and then solve with the point for the a value. So here, it says determine the exact equation of the quadratic function with a double zero at negative 2 and the point 310. So the double zero at negative 2 means that negative 2 is our r and s value, which means it is a perfect square because we have the same factors, right? So what I mean by that is if we have y equals a x plus 2 times x plus 2, that's the same thing as saying y equals a x plus 2 squared. It's the perfect square. Now we're going to plug our values in for our point. So 10 is equal to a times 3 plus 2 squared. So this comes from our point. We'll actually take these two from our double zeros. I get 10 is equal to a times 5 squared, or 10 is equal to a times 25. Move the 25 over. I get 10 over 25, or 2 over 5 is equal to a. Now I can write out my factored form because I know my a value. So my factored form would be y equals 2 over 5 x plus 2 squared. Or I could say x plus 2 times x plus 2. Now standard form, I'm going to expand this. So y equals 2 over 5 times, and I'm just going to use the properties of perfect square trinomials. So x squared plus 4x plus 4. I'm going to multiply my a value through. Y equals 2 over 5 x squared plus 8 over 5x plus 8 over 5. So that is the equation in standard form. Next example, again, same concept, same idea. We're given a different form of the zeros. In this case, x plus root 5, 3 plus root 5 and 3 minus root 5. Those are still our x-intercepts, and we're still given a point. So to start off, y equals a, x minus 3 plus root 5. Let me use square brackets here. And x minus 3 minus root 5. I can simplify this a little bit. Y is equal to a x minus 3 minus root 5. I'm just basically multiplying this this negative 1 through, and then I have x minus 3 plus root 5. This is almost like a difference of squares in a sense that I have one term in the front minus another term, and then one term in front plus another term. So if I want to simplify this, a x minus 3 squared minus root 5 squared, because we kind of see a difference of squares here. We have an a and a b, and an a and a b, and we're separated by addition and subtraction. So difference of squares. I can simplify this now. Y equals a x squared minus 6x plus 9 minus 5. Y equals a x squared minus 6x plus 4. So a lot of work to kind of get down to this endpoint here where it's all simplified. Now we're going to plug in our point. So all the way back up here, I was just plugging in my factor, or my zeros. Now I'm going to plug in my point. Y equals, not y, negative 12 is equal to a times 2 squared minus 6 times 2 plus 4. Negative 12 is equal to a times 4 minus 12 is negative 8, negative 4. Divide out the negative 4, I get 3 equals a. So it's a long way to get to my a value. If I wanted to write out the factored form, I could all the way back up at the top. So factored y equals 3 x minus 3 plus root 5 x minus 3 minus root 5. And then standard, we had it almost pretty much already written out in standard form. That was this last part. Y equals 3x squared minus 6x plus 4. I can multiply the a value or the 3 through. 3x squared minus 18x plus 12 would be our standard form. So again, different ways, given the roots or the zeros and a point, we can determine the a value and then plug that in and expand or simplify to get our factored and standard forms. One application question. So bridges like the one shown often have supports in the shape of parabolas. So we have our line, our bridge, and then we have our parabola supporting it underneath. If the anchors at either side of the bridge are 42 meters apart and the maximum height of the support is 26 meters, what function models the parabolic curve of the support? So what that means is we're going to have our curve somewhere on this graph. We're going to assume that the vertex is on the y-axis. Right? So the maximum height is 26. So we're going to have a vertex at this point of 0, 26. Then tells us that, so let me just highlight that first. So maximum height is 26, and it's going to be at the, we're assuming it's at the vertex because all we're doing is modeling the shape or an equation to determine the shape. It doesn't really matter where it's located because we're not too concerned about that. We're just more concerned about the shape. We then need our R and our S values, our 2x intercepts, and that tells us that the anchors on either side of the bridge are 42 meters apart. So if the vertex in the middle and the anchors are on either part separated by 42 meters, that must mean they are 21 meters away from the middle. So we have our S value, we have our R value. One's at negative 21, 0. The other one is at positive 21 and 0. And this forms our parabola, roughly. So now that we have our roots and we have our point, we can plug this in. Right? This one, let's use function notation just for the sake of doing something different. So f at x is equal to a x minus 21 times x plus 21 f at x is equal to, well, now I can plug in my point. So the function is going to equal 26 is equal to a times 0 minus 21 times 0 plus 21. 26 is equal to a times negative 441. Divide out to get a by itself. Negative 26 over 441 is equal to a. That's now my a value, so I can write it out in factored form first. F at x is equal to negative 26 over 441 times x minus 21 times x plus 21. In standard form, f at x is equal to negative 26 times 441. I can recognize, again, a difference of squares. So this would be x squared minus 441. And when I multiply through, f at x is equal to negative 26 over 441 x squared plus 26. Because we multiply the fractions, and the 441s cancel each other out, the negatives cancel each other out. We're left with positive 26. So again, you might have seen something like this in grade 10. We're looking at a few more complex examples and expanding a little bit further than we might have. We might have been able to come up with the factored form, but now we're taking it a step further and expanding it into standard form. So again, all about recognizing the characteristics of the factored form, plugging the roots in, plugging the points in to determine the a value, and then expanding to find our standard form.